This lesson is titled Applying Linear Functions. Model each situation with a linear function. A lumber yard sells pre-cut lumber at 6, 8, 10, and 12-foot beams. It's $1.20 per foot. So if we want to model the situation, we're looking for an equation. It should involve a couple of variables, one for cost and one for how many feet. And since it costs $1.20 per feet, we can just simply write C, cost, equals 1.2 or $1.20 per foot, 1.2F. That equation is a simple equation that models this situation. Here's another one. A market sells chicken for $2.99 a pound. What would you put for that? We're probably going to need a variable like cost and a variable like how many pounds, maybe P. What would cost equal? In this case, cost would equal 2.99P, or $2.99 per pound. That's the total cost. Here's one for you to try. Suppose an elevator is 400 feet above the ground. It descends at a steady rate of 15 seconds. Excuse me, it descends at a steady rate. After 15 seconds, it is 250 feet above the ground. Your task is to write a linear function for the height of the elevator as a function of time. Go ahead and pause the video and give that a shot. Okay, well let's try a little diagram here and see if we can help ourselves with this a little bit. So it says we've got this elevator that's 400 feet above the ground, so let's let this kind of represent my elevator shaft. My elevator's up here somewhere in that shaft. It's 400 feet above the ground. And let's go ahead and mark that as 400 feet, 400 feet up to there from the ground. Okay, it descends at a steady rate. That's important, a steady rate. Why is that important? Well, because we're dealing with lines here, and y equals mx plus b. This thing called a slope right here, that is a steady rate. The faster we understand what slope is, that it's a rate, the better off we're going to be for math from here and well beyond. All right, so let's see. If we go down for 15 seconds, we're going to be at 250 feet above the ground. So let's say our elevator goes down for 15 seconds, then it's down here, 250 feet above the ground. So this distance is now 250 feet. That's 250 feet. Well, how far did my elevator go? It went from 400 feet down to 250, so the distance that's right here is just 400 minus 250, or 150 feet. So in that 10 seconds, or 15 seconds I should say, in that 15 seconds my elevator moved 150 feet, which means that it was going at 10 feet per second. 10 feet per second times 15 seconds would be 150 feet. So that's my rate. That's this rate right here is going to be 10 feet per second. This b value is just my starting value. It's going to be my 400 feet. So my equation, my linear function, to model the height is h is equal to 10 times t, my number of seconds, plus 400. Actually, no, it's going down. Let's get this right. It's going down. So that we want to make sure that that rate's going down. So we start out at 400 feet high. We go down 10 feet for every second. And there's my function in terms of t. H equals 400 minus 10t. Let's see how that compares with what we should get here. There we go. H equals 400 minus 10t. We'll bring back up our work, and you can compare how we set that up. Here's a couple more for you to try. So go ahead and pause the video and give these a try. All right, let's see. Which graph best models the amount of money in a bank account after the same is withdrawn each week? Well, if we withdraw money, we're not going to withdraw it on a continuous kind of thing. It's going to be more of a unit by unit kind of thing here. A discrete. It's going to be discrete. So it can't be this one because this is going up. We're not going to have more money in the bank if we're withdrawing. It's got to be C, because as we withdraw money, we have this amount of dollars. We take out some money. In the first week we have that much. After 2 weeks we take out some money. We're down the same amount each time. So I would say the answer here has got to be C. Here's a couple more problems for you to try. Go ahead and pause the video and give these a try. All right, let's see what it says. It says some ninth grade students drew the following graph to represent how much money would be in the fund after selling barbecue dinners at the end of a season softball game. What does the slope and y-intercept of the graph mean for the given situation? Well, here's the y-intercept right here. It looks like it's at $50. The slope is just how far this rises as we go from one to the next. And if you look here, it goes over and up. It goes over 1 and up, what, $10. So the rise is 10 over 1. So the slope is $10. Well, what does it mean? Well, it means we started with $50 in the account before we sold any tickets. We sold 0 tickets here. We've got $50 in the account, and we're making $10 per ticket, or we're selling them for $10 per ticket. That's what I would say this means. How about if the graph had the same slope but a y-intercept of 100, what would you conclude? Well, we conclude that we just started out with $100 instead of starting out with $50. And if the graph had a slope of 7.5 instead of the 10, what would we conclude? Well, we're not selling the tickets for $10. We'd be selling them for $7.5 or $7.50. In this you try, you're going to write the slope-intercept formula, the equation for each line. Let's do the first one together, and then you can try the other ones. Remember, slope-intercept is y equals mx plus b. So we need to find the slope, we need to find the intercept. The easiest thing to find is the intercept. It's the point right here. That's too high. So it's going to be y equals something x plus 2. We just need to figure out the slope. And notice how this thing rises and then it runs. So if we can figure out the rise and the run, we're going to have the slope. So we rise 1 and we run over 1, 2, 3, 4, 5. We run 5. So my slope is rise over run, which is 1/5. I can write my equation. Y is equal to 1/5 x plus my b value here is 2. And there we are. Let's check that with what they want us to get. And notice y equals 1/5 x plus 2. Go ahead and pause the video here and you try the other two. And let's see how you do. Let's take a look at the next one here. Let's see, we've got a y-intercept here at -1. Let's see if we can count the slope out. This rises to this point and runs to this point. So how far does it rise? It rises 1, 2, and it runs 1, 2, 3. So rise over run, my slope would be 2 over 3. My y-intercept here, my b, is at -1. So my equation should be y equals 2/3 x minus 1. That should match up perfectly with what they did. Y equals 2/3 x minus 1. If you haven't already, make sure you try 21 before you look at the solution here. All right, again, let's see. The y-intercept is up here at 4, so that means my b value is 4. And to get a slope, I'm going to have to go, always work left to right. So I'm going to work from the left point to the right point. So instead of rising, I'm actually falling, which means my slope is going to be negative. So how far did I fall? I fell 1, 2, 3, went down 3, and I went over 1, 2, right 2. So down 3 and right 2. So my slope is -3/2. So my equation should be y equals -3/2 x plus 4. And again, that should match up nicely with theirs. Good. That's our learning target for this lesson. I'll see you in class.